Hello, quarantines. Welcome back, Academic Astronomy. I hope everybody is being very safe at home and being able to make good use of your time here. Not going to give you a lot to do this week, but I want to start taking you through the notes for section 7, Stars and Galaxies. So what we're going to do, hopefully you have printed out your pack of notes at home. So now I'm going to take you through the first 4 pages of it, just like I would do in class. I'm going to share you some stories, try to make it as interesting as possible, and try to go fairly quickly so you don't have to spend a lot of time sitting there in front of your computer watching it. Then at the very end, I'm going to take you through 10 questions, which you are going to answer in Google Forms. The only trick about it is you're not actually going to see the question in Google Forms, only the 4 multiple choice answers. And that's hopefully to try to encourage you to actually watch this video and go through the notes with me rather than just skipping ahead and trying to just answer things by winging it. So here we go. If you do have your note packet printed out, please follow along with me. We're looking at the brand new notes for section 7, Stars and Galaxies. So here we go. So years ago, before I actually had easy fill in the blank notes, I would always begin this section by asking students, what is a star? And for a lot of you, it was really, really tough to define. People know that stars are up in the sky. They look really bright and they're probably hot. And most people know that our sun is a star, but the only real difference between our sun and the other stars out there is that it's much closer to us. So rather than looking like a little tiny pinpoint of light on the sky, it looks like a really big bright ball. But beyond that, even a lot of adults don't really know a lot about stars. Why are they so bright? Are they on fire? And what are they made of? Are they solid like a hot coal? Well, in reality, this is my homemade definition for stars. It's basically a big ball of glowing gas, or we could say plasma, which is like an electrically charged mix between a liquid and a gas, that's hot enough to begin a very special F word. No, not that one, teens. This one, nuclear fusion. It is a process that makes stars hot and bright. So what I try to do in this section to make students understand stars a little bit better is we liken stars to living things just like you or I. We're going to talk about baby stars being born. We're going to talk about young and middle-aged stars, and then eventually grandparent stars and how stars eventually die out. Now, just so there's no confusion, as far as we know, stars are not actually living, breathing, sentient entities like you or I. But recently, I have seen some pretty wild research where some astronomers are actually testing that just to make sure. They're actually monitoring stars that right now are in very precarious positions, like let's say on the verge of being pulled into a black hole. And they're actually seeing if those stars over time could make independent movements to try to get out of those situations. So probably stars are not alive, but I think it's still fascinating research. And at least for this section, we're going to talk about them that way. So all stars, whether big or small, are born in similar stellar nurseries, like a molecular cloud or a nebula. Over here at the left, you can see just a tiny piece of one of the most famous, beautiful images ever taken by the Hubble Space Telescope. This is a piece of M16, the Eagle Nebula, often known as the Pillars of Creation. And if you look really closely, everybody, you can see little bumpity bumps sticking up off of it. And those little nodules are baby protostars, almost growing out of this tower like little olives on the branches of a tree. Now, I always like to think about a star's life on a seesaw, and it's a constant battle between 2 different forces. On one side of the seesaw, you have gravity. Gravity wants to flip the seesaw its way and crush the star down to nothingness. On the other side of the seesaw, though, you have star energy, the outward push from fusion. Star energy wants to tip the seesaw its way and expand the star really, really big. Well, at least early in a star's life, this existence is dominated by gravity. It's like gravity is the big kid bully on the playground. He is so strong that the seesaw is tipped over his way, and poor little star energy is just up here kicking his legs. He can't even fight back. So this protostar gets squished smaller and smaller and smaller. It gets hotter and hotter and hotter, and then boom, finally, at step 3, core fusion ignites. So for the first time, star energy starts to push back against the ever-present crush of gravity, and our seesaw starts to level out. By the time we hit step 4, equilibrium, the root word is equal, meaning the same. Those forces come into a balance. So anytime you look up at the sun, and obviously if you just learn one thing from this class, don't look at the sun, it hurts your eyes. But anytime you just sort of peek up there, it looks like a totally round, smooth ball where nothing at all is happening. In reality, that could not be farther from the truth. Every second of every day of its existence, our sun is fighting this seesaw battle. Gravity wants to crush it down to nothingness. Star energy wants to expand it really big. And later in this section, we're going to see which of those two forces is going to win out for our own sun. And the answer just might surprise you. So here, everyone, is actually what's going on in the core of stars. This is that special F word called fusion. The root word is fuse, meaning to combine. So right here, you can see the reaction that is happening literally trillions of times every single second inside the core of our sun. Please take a minute and respect this reaction. It's why we are all alive today. Were it not for this, the sun would not be hot or bright, and life on Earth here and throughout the cosmos would not be possible. Now let's talk just a little bit about fusion. This is not actually what our nuclear power plants do. Our power plants do something called fission with an I. The root word is fissure, meaning to split apart. Our nuclear power plants take big atoms like uranium and plutonium, and they split them apart into what's called daughter product. And it does create a lot more energy than burning fossil fuels. But there are some precarious trade-offs with nuclear fission, like nuclear reactor meltdowns that we saw at Chernobyl, almost saw at 3 Mile Island in Pennsylvania, and are currently seeing with the Fukushima power plant on the shore of Japan, which is a really big disaster that the media basically just stopped covering. Fusion, though, does not have any of those issues. It's very clean and very safe. And if we could ever figure it out here on the Earth, it would absolutely solve the world's energy needs. So basically what's going on, everybody, is every second of every day, our sun is taking 2 atoms of hydrogen, atomic number 1, and smashing them together in all this heat and pressure to make 1 atom of helium, atomic number 2. Now, looking at this reaction, you might think to yourself, well, wait a minute, how in the world does this generate energy? Because normally, anytime we're combining things to make bigger things, that actually uses up energy. Well, it's actually based on something called the nuclear binding strength. So basically, all you need to know, it takes slightly more energy to keep 2 little hydrogen atoms together than 1 slightly bigger helium atom. So when you combine the hydrogens to make the helium, it releases a neutron and this excess energy. That is nuclear fusion. This little neutron will then cruise around the core of the sun. It'll find another hydrogen called a deuterium, 1 proton and 1 neutron. That'll smash together to make a tritium, 1 proton, 2 neutrons. That'll then smash together to make a deuterium, to make a helium, kicks off a neutron, and on and on and on, trillions of times every second. This reaction, everybody, is so prolific. I've actually read estimates where our sun loses anywhere from 2,000 the whole way up to 200,000 tons of mass every single second. And yet our sun is so big, it's been doing this for about 5 billion years, and it probably has enough in the tank to do it for another 4 to 5 billion more. So just one last thing on nuclear fusion, which I find fascinating. Back when Mr. Krug was growing up in the 1980s, they actually thought by the year 2000, we would be able to do this here on the Earth. And if we could, it would absolutely solve the world's energy needs. For example, with this one reaction that you see here, there is enough energy in a single glass of water to power the entire city of Los Angeles for a full calendar year. So how close are we? Sadly, officially, not very close. Teams of physicists around the world build what are called torrid reactors, and they try to actually make this reaction happen. Now, way back in the early 2000s, I was lucky enough, while giving a tour to a high school student of my college, to meet with her dad, who is a nuclear physicist, who actually worked with a team trying to do this here on the Earth. And he said to try to do it, they had to build what looked like a large metal donut. But this would be no ordinary metal donut. It would be about as big as our planetarium classroom. It would be hollowed out inside. And the walls of the donut, he said, had to be at least 5 feet thick of solid steel on both sides. And so he said inside the donut, they would get a superheated plasma swirling around. And they would pump more and more and more energy into it and get the temperature hotter and hotter and hotter. And he said for a few split seconds, this reaction would actually happen inside that metal donut. It was nuclear fusion. But he said there were 2 big problems with it. Number one, the reaction was not efficient. They had to put more energy into it to get the plasma hot enough than they got back out from the nuclear fusion. So they actually lost energy. But reason number 2, and this is why I still share this story, he said it would get so hot that after only 2 trial runs, the walls of the metal donut would become brittle to the heat. And once it cooled down, they would just crumble to the touch. So then they would have to build a whole new metal donut and start over. So think about that. 5 feet thick of solid steel. That would be thicker than the hull of a battleship, and it would just become brittle from the heat of fusion. So some physicists are actually looking to what's called cold fusion, which is basically doing this reaction at much, much lower temperatures. And if we can figure it out within our lifetimes, it could solve the world's energy needs. So let's talk just a little bit about the property of stars. The diversity of stars that we have in the sky is more beautiful even than the diversity of humans we have here on the Earth. They all begin in a similar way inside stellar nurseries, but they're going to diversify very quickly in all of these different properties that you see. So first, let's talk about mass. The range of mass of stars is absolutely incredible. There are stars out there that are up to 2,000 times bigger than our own sun. So if you look at this diagram, which I showed you earlier in the year, here is our sun, and then we have some stars that we've learned this year. Sirius and Pollux in the wintertime sky, and then Arcturus, which we are just starting to learn in the skies of spring. There are stars out there even bigger, like Betelgeuse and Antares, known as red supergiants. These are stars so big, if you put them in our solar system in place of the sun, they would actually engulf all the planets out past Mars. Mercury, Venus, Earth, Mars, poof, just incinerated in these mighty stars. On the flip side, there are some stars so small, you could actually fit them between Altoona and Tyrone. These are stars less than 10 miles wide, so massive we're going to see they can even implode and collapse under that crush of gravity and form black holes. Okay, these next 2 properties are very, very consistent. And what that means is we have a relationship between the 2, and that is color and temperature. If you know one of them, you'll automatically know the other. So from this table, you can see that the hottest stars by far in the sky are blue or blue-white. Then we have white, and then notice our sun, a yellow star, is about average. That's going to be a common theme throughout this section, everybody. Even though our sun feels special to us, it's actually very plain and regular, like a lot of stars on the sky. That might make you feel a little bit bummed out because as humans, we like to think that we're special. But think about this. If our sun is average and we are here, that means that there's conditions that are just right for life throughout the Milky Way and the cosmos. So it's actually very exciting. Then stars cooler than our sun are red-orange or orange, and even cooler ones are red. Now, when you go outside at night and look up, almost all stars to your eyes actually appear blue or blue-white. Understand that's not really an accurate representation of what's up there. The human eye is a little bit biased, and we can see high-frequency colors like whites and blues much more easily than lower frequency colors like orange and red. So if we could actually see all colors of stars equally on the sky, there would be far more red stars than anything else. So far, so good. Everything's been pretty smooth until we get here to brightness. Brightness is the one sticky wicket with star properties because it factors in so many different things. What we can see from Earth as far as star brightness depends a lot of things. It depends on letter A, the size of the star. Larger stars tend to be inherently brighter than smaller stars. It depends on letter B, the star's actual brightness. Some stars are just inherently brighter than others. Or how about letter C, the color? As I just mentioned, your eyes tend to see blues and whites better than you do oranges and reds. And finally, the real monkey wrench in the work here, everybody, is apparent brightness. The root word is appear. It's how bright a star looks to us because they could be at very different distances from the Earth. So sadly, we can't just go outside at night, look up and say, oh, that star is very bright. It must be very big. Or that star is very dim. It must be very small. There's a lot of different possibilities here. So because of all this trickiness, astronomers have 3 different terms for brightness. So the most common one that you're actually already familiar with is apparent brightness or apparent magnitude. The root word is appear. So this is how bright the stars appear to us because they're at very different distances from us. If you check out this simple little diagram I've made here, you can see the stars that are closer to our dude or dudette on the Earth appear very, very bright, but the ones that are more distant and far away appear much, much dimmer. This is what we see when we go outside at night, or when we are back in the Neil Armstrong Planetarium, when I bring down the lights and put up the stars. This is what we're seeing on the dome is apparent magnitude. But one thing science likes to do, everybody, is they always like to level the playing field so that comparisons can be even. And that's where we get absolute magnitude. I often call this the police lineup of stars because, as you might know from watching detective or crime shows on TV, if police apprehend a suspect and they bring a witness in, what they'll often do to try to strengthen their case is they'll stand that suspect right beside other similar looking people for an even comparison. And then if the witness can pick out still who actually did it, it strengthens their case. So much the same here with stars. This is basically a hypothetical. It's how bright stars would be if they were all moved to the same distance from the Earth. And the arbitrary distance that astronomers have chosen is 10 parsecs. You might remember parsecs from section 1. It's a little bit bigger than a light year. In fact, each parsec is a little over 3 light years. So all you really need to know is the ballpark distance is about 30 or 33 light years away. So if you look at this diagram here, everybody, I tried to make it sync with the diagram from the previous page. So notice what's happened here. On the previous page, we had all the stars at different distances. Now we've hypothetically taken them and moved them in a straight line. And we can see now that this star, which appeared very bright, is actually quite dim when moved to a standard distance. It also turns out this star, which appeared dim, was only really appearing that way because it was very far away. If we move it to a standard distance, it's actually at least an average brightness star. So that's absolute magnitude. Finally, the last brightness term you might see with stars is luminosity. Now, this is the one time we totally throw distance out the window. It is only the size and the actual temperature of the star. We will call that a star's true brightness. So beyond these properties, we also have density. Just like planets and most moons, stars tend to get denser as you get into the center. We already know from section 5 that our sun has a core just like the Earth, and that's the only place where it's actually dense enough for nuclear fusion to take place. Now for composition, we're going to see that here stars diverge. Larger stars are going to lead very different lives than average or smaller mass stars than our sun. So we're going to see in just a little bit that supergiant stars, really massive stars, are going to ravenously chew through their fuel, and they can make bigger and bigger elements the whole way up to iron. The famous astronomer Carl Sagan always liked to say that we are made of the stuff as stars. Think about that. Right now, even the iron that is coursing through your veins at one point billions of years ago was forged in the nuclear furnace of a supergiant star. For stars like our sun, though, they will only actually fuse up to carbon, one of the greatest life-giving elements in the universe, before they burn out. All right, thanks for sticking with me. The very last thing we want to talk about for this first section is letter D, the Hertzsprung-Russell diagram. Sometimes, everybody, science can actually be very, very cutthroat. And scientists and astronomers often snake each other to try to get credit for discoveries first. This was one special rare time where that did not happen. A scientist named Hertzsprung and a scientist named Russell were both working on a similar idea around the same time, and they found out about each other. So rather than one of them trying to get all the credit, they decided to share it, and they put both their names on it. So this diagram that you see became known as the Hertzsprung-Russell, or HR diagram, and it's quite possibly the most epic, awesome diagram in all of astronomy. What they are doing here is they are classifying all stars in the universe according to just basically two simple things: the brightness, and so over here we see absolute magnitude, which is a term we just learned for brightness. You will also see this diagram sometimes, and it'll say luminosity over here. About the only brightness term you'll never see on that axis is apparent magnitude. Because remember, that's the stars at different distances from us. And the whole point of this diagram is to level the playing field for an even comparison. Remember too, as we look over here, magnitude is a little bit funny. The lower the number, the brighter the star. So when we see negative numbers up here, these stars at the top are truly bright. When we see high positive numbers down here, these stars at the bottom are truly dim. On our other axis, which sometimes they'll show you at the bottom, sometimes at the top, either way it's the X or horizontal axis, is our temperature. So notice this is a lot like an XY graph in math, but the only real difference is notice the temperature is actually increasing to the left rather than the right. So here on this diagram, our hottest stars are over here on the left and our coolest over here on the right. And keep in mind with stars, cool is a very relative term. This isn't like ice cubes or snowflakes. Even cool stars are still over 3,000 degrees Celsius or Kelvin. So just a couple things to note on here. I like to think of this diagram as basically two sets of overlapping halves. Here we have the bright half. Down here we have the dim half. Over to the left, we have the hot half. Over to the right, we have the dim half. So where the corners overlap, we can tell what the properties of stars would be. And you can see we have four main star groups here. We have main sequence stars like our sun. This diagram, or I'm sorry, this group snakes through the middle of the diagram, and it composes most of the stars on our sky. We have supergiants at the very top. All of them are very, very bright, but you can see the blue ones are hot and bright. And the red supergiants, the real monsters out there in the cosmos, they're massive, are very, very cool and dim. Right below that, we have red giants. And even though they sound similar to the supergiants, we are going to see they live very different lives. In fact, even though our sun is right here right now, someday it's actually going to grow to expand to become a red giant. Finally, an ending point of our sun, red giants are eventually going to poof, blow off their outer layers, and what will be left behind is a white hot core called a white dwarf. Even though they are very, very hot, because they're so very small, they're actually quite dim, so they show up down here in the lower left corner. So wrapping things up, as we look at the colors, which they'll either show you across the bottom or the top, you can see they coincide well with our temperatures. Blue are the hottest stars, so we see them over to the left. Red are the coolest stars, we see them over to the right. And yellow stars like our sun are right in the middle. You might also notice 7 letters here that initially don't seem to make much sense. O, B, A, F, G, K, M. These are the spectral classes of stars. And here in academic astronomy, we do get into that just a little bit more. Spectra is awesome. It's basically the unique light fingerprint of stars, and astronomers can tell a great deal from it. Here in our high school class, I probably do a disservice by not teaching you more with spectra, but it can be very, very complicated. So here's a basic crash course. Stars will have different spectra based on what elements are inside them. It turns out that when light is emitted from a star, whatever elements are present in it tend to absorb out or remove special frequencies relating to those elements. So astronomers can actually use spectra to tell what a star is comprised of, which is really awesome. So here's a table. Once again, you can see O, B, A, F, G, K, M. And the silly way that astronomers remember this is O, be a fine girl, kiss me, or O, be a fine guy, kiss me. O, B, A, F, G, K, M. You can see our yellow sun is called a G-class star. It's actually a G2 star. So here's where our sun would be. Finally, in the life column, these numbers look small, but notice at the top our heading is 10 to the 6th. So this is actually to the millions of years. So for our sun, 9,000 million years would be the equivalent of about 9 billion years. Even little tiny red dwarf stars, potentially we think, could live up to about 200 billion years, which is longer than the existence of the entire universe itself. The wild thing though, look how short-lived the very massive stars are. The truly huge stars, like class O stars, actually live less than 2 million years. And that's rather surprising because we would tend to think the bigger stars will live longer because they have more fuel. But overall, it seems to be quite the opposite. The massive stars chew through their fuel ravenously, and they live a very short time before they kaboom and supernova, which we'll learn about in the next lecture. But very small stars, it's almost like they know they don't have very much to begin with, so they use it very, very slowly and sparingly, and they can live billions and billions of years. So the rest of this page just shows you some nice diagrams about the differences between these 7 color classes of spectra. Okay, I think it's time for our 10 questions. So right now, if you could, feel free to pause the video and open up Google Classroom and find the 10-question quiz on this first part of the notes. You're welcome to actually use your printed out notes to help you find these answers. And you'll also see that this quiz is not locked. So you can actually go back and forth between this video on YouTube and Google Forms. So I will ask the questions. You actually need to hear the words coming out of my mouth, but you'll see the 4 multiple choice answers for 1 through 10. So here we go. Good luck on your quiz. As long as you paid attention, I think you're all going to do really, really awesome. Question number 1. What is a large ball of glowing gas hot enough to begin nuclear fusion? Feel free to pause the video and look at your choices for Google Classroom and pick the correct answer to number 1. Question 2. This catalyst of the universe powers the interior of stars and gives us life. Number 2. Number 3. Every second of every day, stars like our sun fuse together 2 atoms of blank, atomic number 1, to make 1 atom of blank, atomic number 2. Question number 3. Question 4. What physical property of stars directly relates to temperature? So for example, because our sun is 6,000 degrees Celsius, we know that it must be what? Question number 4. Question 5. When you go outside at night and stare up at the stars as they appear at different distances from the Earth, Which type of magnitude are you observing? Question number 5. Question 6. Average to low mass stars like our sun will not create very heavy elements within their lifetimes. In fact, they only fuse up to the element blank. Question number 6. Question 7. The Hertzsprung-Russell diagram is legit. What star group snakes through the entire diagram from the upper right corner to the lower left corner? Question number 7. Question 8. Speaking of the Hertzsprung-Russell diagram, what property would stars in the lower left corner of the diagram have? What properties would they have? Question number 8. Question 9. Compare the HR diagram to spectral classes on the following page. This was the last page we looked at together. What spectral class would red supergiants be considered? Question 9. And finally, question 10. What spectral class is our own yellow sun? Question number 10. Teens, you've been excellent. Thank you for joining me for the first part of the notes for section 7, Stars and Galaxies. Make sure that you've answered those 10 questions in Google Classroom. And once you're done with section 1, you can go on to section 2 of our video conferences together once you complete the quiz. Thank you, and we'll see you again real soon.